Asteroids.java. So this is launches the game. So you get either when you pick classic, it launches the regular controller.
All right, let's get started.
Oh no. I mean,
Okay, so you've got the final assignment out. PS11 is out. There were a few students who appears to me missed the PS11A deadline, but of signing up for a group. So let me just repeat, you need to be part of a group to do PS11. So if you haven't signed up for a group, you need to do that. It can be a group of one, but you still need to sign up for a group. This week, you and your partner, if you have one, need to make an appointment to meet with a TA. We've basically taken all their usual consulting hours and split them up into 10-minute blocks. And you need to meet with the TA and show them that you've made progress. And what the TA will be looking for is that they want to see that you've done 4 things from the list of things to do. And so that's worth 40 points out of the 200 points for the final assignment. So be sure that you do that by Friday at the latest. And they're not going to be anybody staying up till midnight to do this. So be sure you make an appointment in advance and then go. If you have a partner, you need to have both people, both partners need to show up. Okay, any questions or problems about anything? Yes?
So you go into Scheduler, and then it'll say like PS11B meetings with whatever TA.
Right. So
you can like click on that, and it says you can sign up for this, but that doesn't do it.
It doesn't do anything. Well, I know who has successfully signed up.
just marks it as reserved.
Okay, I just have to look at what's happening for you. I don't know what to say.
I'm gonna have to change my some hours to Friday because I have to leave early.
So yeah, so the schedule's, Stephan was saying he may change his schedule slightly to have hours later in the week. Any other questions? Yes?
Wait, did you say both you and the partner have to go?
Yes. Yeah. If you show up without your partner's not going to get 40 points. Yep.
For someone who only can work from a desktop, is there a good way to send our in-progress project, I guess, to the TA before the meeting? Like, because we can't bring the project to them, show them.
I wouldn't send it to the TA. You could just bring it on a USB stick or something.
Or just bring it up on the computers in the K lab. Just put it on your own drive, and you can just have it running, ready for us when we come.
Any other questions? Okay, the lab tomorrow will be devoted to nothing formal planned. It's just it'll be a chance for you to get questions answered and work on your project with TAs there. Yes?
Are you going to be posting a review for the final?
I think it's in fact, if I'm not mistaken, it's already posted, but I may be mistaken. Actually, I don't think the review is posted yet. The sample exam is posted.
Thank you.
So next week, the lab on Tuesday will be going over a sample final exam. And then the last lecture on Wednesday will be a review for the final. And then the final is 2 weeks from tomorrow. It's Tuesday the 12th at 3:30. Okay. I haven't figured out exactly how we're going to do this yet, but I'm going to have the exam in 2 rooms. I thought it was too crowded in here last time. So I'll be asking some of you, probably based on either your last name or your unit, to go to a different building in a different room to take the exam there. So we'll have some here and some there. But more news about that later. All right, what I want to do today is I want to talk in more detail than I have in the past about the Java memory model. And the idea is, when your program runs, Java has to keep track, as the program is running, has to keep track of the values of variables, and it has to be able to change variables, create objects. That's all done in the computer's memory. And there's a pretty standard way that programming languages manage memory to do this. So I say it's a Java memory model, but it's a memory model used in most programming languages. I want to emphasize at the start that it's just a model. It's not, I'm not trying to show you every detail of how a program is dealt with at runtime. I'm just trying to give you the big ideas. But this really pays off as you go on and take other courses, if you can understand what's going on in memory, what's going on behind the scenes there. So I'm going to switch over now. Can you switch me over? To the laptop here. And what I'm going to do is demonstrate what happens when this little program right here executes, this main method. So what it does, as you can see, it creates an empty myArray list. Then it adds 5 numbers to the end of the list. So it adds the number 0, 1, 2, 3, 4, 5 to the end, 0, 1, 2, 3, 4 to the end of the list. Then it sets the thing at index 3 to 8, and then it removes the last element from the list. So we're going to see what happens as the program runs. Now, the rest of the code for the class is down here. Here's the constructor. So that's one thing that we call. You don't have to memorize this because the code will show up on the slides I'm about to use. But there's the constructor. There's the size method. There is something that adds at the end, add last. You'll be seeing that. There's remove last. Get, I don't believe we're using. The set we are using. So we're going to see how these, what happens as the main method runs and calls these. So I'm going to switch to this right here. Okay, so that thing at the top, that little area up at the top is meant to represent the memory available to a running program. Now what needs to be stored into that area of memory? Yeah?
The value of the variables?
Okay, so the values of variables have to be stored. What else needs to be stored? How else would memory be used by running a program? Yeah?
The instance variable.
Okay, instance variables have to be stored somewhere. Yeah?
I'm not sure, but the current line of the program?
Okay, so you have to, that's called the program counter. So yeah, you have to know what line of code is being executed right now. Yeah?
Just the code in general has to be stored somewhere.
Say again?
The code in general has to be stored
Okay, the code itself that executing has to be stored somewhere. So that pretty much covers it. Now I'm not going to be worrying about, one thing I'm going to abstract away is the program counter. We won't talk about how the program keeps track of what line of code it's operating on. We can talk about it, but it's not illustrated. But essentially, the code has to be stored somewhere, so I'll store it right there. Then the rest of memory we can divide into 2 parts, the stack and the heap. And so the code is stored in memory. The stack is where local variables and parameters go. And we're going to have the stack is essentially a data structure, a runtime data structure the program uses. We're going to have it growing from left to right. And so when a method is called, it gets a little slice of memory on the stack called a stack frame. And the stack frame contains the local variables and the parameters for that method. And so as methods are called, stack frames are pushed onto the stack, and you'll see it grow. So let's say that method calls another method. Okay, it gets a little bit of memory for its parameters, local variables. And then that calls another method, and that calls a 4th method. So the stack can grow that way. Every time a method is called, a new stack frame is pushed. Now there's a limit. You can run out of memory if you keep pushing stack frames. And when would that happen? What's a scenario in which you could end up running out of stack? Yeah. Well, not an infinite loop, because an infinite loop will use a lot of time, but it's not creating any new stack frames. It's close though, yeah?
Infinite recursion.
Infinite recursion. So if you don't have a base case in your recursion, say, and it just keeps calling without ever hitting a base case, every call to the method will create a new stack frame. So if a recursion goes 10 levels deep, you've got 10 stack frames, because you've got 10 sets of variables to keep track of. If the recursion never ends, you'll eventually blow through the stack and the program will crash. But what typically happens is we call some methods and eventually one returns. So when a method returns, you don't need the storage anymore for the local variables and the parameters for that method. And so it comes off the stack. So now we've shrunk down to 2 stack frames, and then maybe the second method calls another method. And typically, if you watch the stack, it'll grow and shrink. Okay, so that's one place. Now, what is there to keep track of besides the code and the local variables and parameters for each method? Yep.
The variables.
Well, what variables? You've got the local variables and the parameters dealt with in the stack there, the yellow part, yeah. Objects, okay? Objects, because they can be shared, go into a different place. So objects, every time you call new, every time you use new, the keyword new, an object is created not on the stack, it's created out in what's called the heap, or free memory. And what's often done is you got the stack growing in from one side and you got the heap growing from the other. And they meet in the middle. Hopefully they don't meet. Hopefully they stay out of each other's way. So essentially, every time you do a new, a chunk of heap is allocated for that object. So we just created an object. We create another object. We create another object. Now what just happened? How did that space open up? Yeah?
Was the object not needed, so it got rid of it?
Okay, that corresponds to the Java discovered there was some object on the heap that wasn't needed anymore, and it was garbage collected. So that opens up space on the heap. Now there's some languages, like C++, where there isn't garbage collection, and it's the programmer's responsibility to say, I don't need this object anymore. So there's a condition to new, there is delete, to get rid of objects. And that's a place that C++ programmers can make errors, either deleting something that is still needed or failing to delete something that's no longer needed, which you folks don't have to worry about in Java. That's taken care of for you. So the stack is nice and compact. There are never any holes in the stack. It grows and shrinks, but it's always solid yellow. The heap, Swiss cheese, it's full of holes. So that we just allocated an object, and there another one got deleted, got freed up by the garbage collector. So the next one can go back in part of that hole that was there. Now we allocate another object that didn't fit into the available space. Now the hole opens up there. Okay? Now, most garbage collectors, in addition to finding, getting rid of unneeded objects, will also compact the heap. Actually move the objects around so the holes disappear. I'm not illustrating that. Yeah?
So assuming that there are some holes and the stack is full, will the stack be able to use the holes, or are those for the heap only?
No, he's asking, let's say the stack grows up to where the heap is and there are holes in the heap. Now the stack can't skip and fill in a hole somewhere. The stack wants to be solid. So what is it about stack frames that makes it so that they get pushed and popped if there are not any holes in the stack? You're never getting rid of, say, this stack frame before we've gotten rid of all those stack frames. Whereas with objects, you end up with holes. What's different between stack frames and objects? Okay.
Because new stack frames only when there's a new method call.
Okay, so he said, new stack frames are pushed when you make a new method call. That's why they sort of grow. What's the other, somebody else tell me the other thing that makes sure that holes don't appear. What would prevent us from getting rid of, why would this stack frame right here that I'm illustrating with this red dot not go away until everything to its right had gone away? Yeah? I mean, back there.
Because of the way that it returns, it's a call, and then it has to return.
Right. So basically, this here represents a method that was called, which called this method, which calls that method. Now, of those three methods, which one has to return first? This guy right here has to return first. So that's why a stack is used to keep track of the values of variables with method calls, because they follow what's called a stack discipline. The last one on the stack is the first one off. What is it about objects, though? Why do holes show up here? Yeah?
because the order in which objects become like not useful anymore won't necessarily be the same as the ones they created.
Right. So we can allocate objects. You know, if we never had to get rid of objects, we could fill them in from right to left in a solid fashion. But at any time, any object, no matter how long ago it was allocated, might become useless. It just depends what your program is doing. And that's why a hole could open up here while there's still objects to the left. So object allocation and freeing do not follow a stack discipline. So we use the stack where we can, we use the heap where we have to. Now, yeah?
Would there ever be a time where the stack would push and cause the heap to fill in those spaces?
Well, if you're following this sort of design, you know, if the stack wanted to run to the heap, that would trigger the garbage collector to compact the heap. And then the stack could continue to grow.
Okay.
Now, in Java, I think it's more typical in Java that the stack just has a fixed size, a fixed maximum size, and the heap has the rest of memory. So there's not this trade-off. Yeah?
Like the programs that you're writing right now, like unless you may end up making an infinitely recursive call, do we have to worry about this?
Unless you have an infinite recursion or a very, very deep recursion, you're not going to run out of stack. You know, you know, if you get up around 100,000, I'm just estimating, 100,000 or so stack frames is going to the stack in Java. But you're not going to get there without a big pile of recursion. And it's adjustable. You can, when you, you can customize the Java runtime so that it allows a larger stack. It takes more memory and gives you a larger stack. So you can make it as large as you need. Okay, so that's just a very high level idea what's going on. So we got variables in the yellow. Rather, I should say local variables and parameters in the yellow. We got objects in the brown. Now, let's see how that really works. So we're going to go through that main method and see what happens. The first time through, we're not going to worry about the heap. We're not even going to worry about the values of variables. I just want to see the stack frames come and go and see what's in them. So there's our stack. I'm going to have it grow now from bottom to top, just because it fits my slide a little better. So we just called the method main. And whenever a method is called, a stack frame is allocated. And the stack frame, there's a spot in the stack frame for each local variable and parameter. Now, typically, main would have an array as a parameter, args. Since our program doesn't deal with it, I just took it out to avoid clutter. But you see, we have list right here is a local variable, and I is a local variable, so they both show up here. Now, strictly speaking, it's not just when you call a new method that a stack frame is pushed. When you enter a new scope, we ought to be pushing a stack frame as well. So really, this I is declared inside the for loop. And you could imagine having, since we have these braces here, you can imagine having a stack frame with just list, and then another stack frame is pushed just containing I. But I'm going to avoid that detail too. I'm going to put all the variables in the method into the stack here, just to keep things simple. Okay? Now, what's going to happen next? When will the stack be modified? Now, we're not talking about, I'm not going to worry about the values of I and list here. When will a new frame be pushed? Yeah?
When you remove something.
Okay. So when I do this right here, I'm going to have to involve a constructor, right? We're going to have to call the myArrayList constructor right there. So let's see what happens. So we have our stack frame there for main. And I'm highlighting in green there. Green means we're about to execute the statement. Red means we just finished executing the statement. So the first thing that has to happen is we have to create that array list, that myArrayList. What's the purpose of storing I in list right there? How is that used? Okay, he said, does it make it a quicker way to get the value of a variable? It's just the way to get the value of a variable. When your program is running and it needs to store 0 into I, it stores it right into the stack there. When it needs to look up the variable of I, the value of I, it goes and looks in the stack as well. So it's just, programs have to know the values of their variables. That's how we do it. Why don't, instead of bothering with a stack, why don't we just have a table for each method? So main will have a table containing I and 0. And every other method will have its own table containing space to store its variables. Why not do it that way instead of having the stack grow and shrink? Seems like that'd be more efficient. Yeah?
Sometimes methods need to call other variables from different methods.
Well, he's saying methods need to look at variables from other methods, but that's not the case. Main here cannot look at a variable inside of a constructor. It cannot look at a variable inside of add last. A method can only see the variables declared in them. So that's not it. Why can't you just have one table per method? Yeah?
Well, it's, because it would be very complicated setting out tables all around in memory. Amplify the Canvas keys thing where you'll have one thing here and then another thing here. There'll be a lot of gaps all across that memory.
Okay, so I have to call that sort of a speculation that it would be hard to manage, because actually I think it wouldn't be that hard to manage. I think you could just start out by allocating a table for each method, just pack them all together. If you have 10 methods, you got 10 tables and you're done. Yeah?
I'm not entirely sure how, what's the difference between the stack frames and the methods, the tables you're suggesting.
The table for main would contain I and list. So just imagine, instead of having these stack frames that you create, that you push and pop, just before the program runs, you set up a table for each method. Yeah?
The tables would need to be different sizes because some of them will call lots of variables, and other ones will call not
Okay.
many. So you have like some that have empty space and some that didn't have enough space.
Well, she's saying that the tables would have different sizes, and that's true. But you could still pack them tightly. Yep?
That may not be absolutely space efficient. If we set up all the tables at the front, we might not have tables that we use until several hundred lines of code later.
Okay. So that's a good observation, that some, how many methods are there? Well, if you look at your program and you look at the entire Java library, you could call any of those methods. You certainly don't want to set up a table for methods you're not going to call, but we really haven't got to the heart of the matter yet.
Wouldn't that just take up a lot more extra space than it needs to?
Well, it does create, it takes up extra space. It would take more space than the stack, because the stack is just space for the methods that we're currently in the middle of using. But there's a reason why it doesn't work beyond that it's not space efficient. Yes?
Is it the garbage collection?
No, it has nothing to do with garbage collection. That's a heap concern. What's one thing that could wreck this idea? Yeah?
So, the order by which methods was called.
What do you mean by the order in which methods are called?
So, as you demonstrated, it's you have a method which calls a method, which calls a method, which calls a method, and that's how they stack on top of each other. And if you just have tables, then you wouldn't have that idea of stacking.
Well, right, if you had tables, it wouldn't have stack, but it'd still be a way to look up the variables. I'll tell you, Fortran, back in the day, this is how it did its thing. It just had a table for each, they didn't call them methods, but a table for each method. What was Fortran missing that Java has that makes the stack necessary? I bet you someone's thinking it, but you're not sure. Yeah?
Recursion?
Recursion. Why does one table per method not work when a method is recursive? So F calls F, calls F, calls F. Why won't that work? Just have one table. Yeah?
Because each recursive call needs its own table.
Right. Each recursive call needs separate space to store the values of its variables. Now, if it's just now occurring to you that this is true, that each time you call a method, it gets its own set of variables. It doesn't share space with the previous calls to F. If it's just now occurring to you, that may be why you don't understand recursion. Because if your model with how memory works is that each method sort of has a table to keep track of its variables, one table, recursion wouldn't work. The methods would interfere with each other. The recursive calls would interfere. Recursion works because there's a stack. Now, Edsger Dijkstra is a famous computer scientist. He died a few years ago. And when you study algorithms, you'll hear that name. But Dijkstra was a graduate student that implemented a language called Algol 60. And Algol 60 is a precursor to a lot of languages we use today. And he introduced this idea. He sort of came up with this way of implementing programming languages. And he looked at the language definition that had been come up with for Algol 60 and saw that it didn't prohibit a method calling itself. And so he just assumed, he made this controversial decision to let Algol 60 be recursive. And so he had to develop this idea to make recursion work. So the stack is what's needed to support recursion. Fortran, back in the older versions of Fortran, did not support recursion, so it wasn't an issue. Anyway, we're about to call the constructor. First thing we got to do is just allocate space. Well, we're not talking about the values. So let's see what happens when we call the constructor. We call the constructor, we just pushed a new stack frame. So I want you to notice a difference between the dark lines here. The dark lines separate stack frames. The light lines separate variables in the same stack frame. So this is a stack frame right here. And where did this come from? Why is there this? I don't see, well, I do see this. Yeah?
It's a temporary variable that made while it's creating the value that's going to be given to this.
Well, it's actually a parameter that's passed to the constructor. I would call it a temporary variable. I guess it is temporary, yeah? Eventually, it will contain a reference to the object on the heap, the myArrayList object that's being initialized. But every constructor and every non-static method takes an implicit parameter, this. Even though you don't see it in the definition, you don't see it being passed as a parameter, it's implicit. So every stack frame for a constructor and every stack frame for a non-static method will have this, the object in which the method was invoked, or in this case, the object in which the constructor was invoked. Okay? Now, what's going to happen now when myArrayList returns? Okay?
This stack frame will close.
Okay, so that stack frame will disappear. Now my note there says the method or constructor only needs to look at the topmost stack frame. That's a very important point. That constructor never needs to look down here at I and list. They're invisible to it. Java won't let you, if you tried to reference I or list from that constructor, it wouldn't compile. So all that a running method or constructor needs to know about is where the topmost stack frame is. It doesn't matter what's down below. So what good is that stuff that's down below? If the method that's running can't access it, why do we need it down there on the stack? Why can't we have gotten rid of it? What good is the bottom stack frame?
Well, once whatever method we're on returns, we're going to care about what was under it, what method called it.
Right. So as soon as this constructor returns, boom, we're back in main, picking up where we left off. And main expects to find its variables there on the top of the stack. So we pop away the constructor's frame because we don't need it. Now we're back executing inside of main, and our variables are right on the top of the stack where we expect them. Okay? So that's why this works. Now, in my diagrams, I'm writing I and list in the stack. In a real language implementation, they wouldn't appear there. You just have the values of I and list on the stack. And the way your program runs, when it wants to find I, it knows that I is stored 0 bytes from the top of the stack. So the program has access to the address at the top of the stack, and it knows I is going to be right there at the top of the stack frame. It knows that list is going to be 4 bytes down from the top of the stack frame. So I is right here. If this is the top of the stack, I is 0 bytes from that, and list is 4 bytes from that. Why 4 bytes? Where's the 4 bytes come from? Yeah?
Size an integer.
Right. 4 bytes is what it takes to store this integer right here. So you got 4 bytes for I, and then you've got however many bytes you need for list. So when this code is compiled, it's not going to say list. It's not like this code has to go and look for list in the stack. It's going to know that whatever reference comes back from my array list needs to be stored at a spot 4 bytes down from the top of the stack. So it just plops it there. So all we have to know is where is the top, and we index off it. It's almost like the stack frame is an array. Okay? What's the next change that's going to happen to the stack? Yep.
This list is going to get bigger because you're setting things in it now.
Yeah, but again, we're not modeling what's happening with these variables. We're just trying to see how the stack frames are created. So when will the next stack frame be pushed or popped? Yeah?
When addLast.I runs.
Okay, eventually we get down here and call list.addLast. And so when we call list.addLast, that shows me we're about ready to call it. Then we call it, it pushes a stack frame. So why are E and this in the stack frame for addLast? Okay.
Because addLast gets its own stack frame, and that gets this as the implicit parameter, and E as something that it defines.
Right. So E is a parameter. This is the implicit parameter. There are no local variables, so we get E and this. And so when it needs to look up E, it knows it's at the top of the stack frame. It knows that when it needs to look up this, it'll know that it's 4 bytes down. That's something the compiler can figure out in advance. So the names aren't floating around. We're just putting the names in the stack so we can make sense of them when we look at them. Okay? All right? What's the next stack operation that's going to happen? I want to get a different volunteer. I need someone else brave enough to answer. Oh, you're hardly different, but you're someone raise your hand that hasn't raised your hand today, okay? Update list. Well, we're just interested in method calls at this point, because we're not looking at what's stored in the variables. So someone tell me, what's the next method call?
Could you repeat the question?
Okay. We've just called addLast. And now it's going to execute its code. Yep.
Well, go ahead, got it.
They did the next iteration of the for loop and call addLast again.
Well, yeah, but we're not in the for loop now. We're in addLast. So first thing addLast is going to do is compare this.count to this.else.length. Yeah. What happens next?
And it calls arrays.copy of.
It may or may not call arrays.copy of. It turns out it won't, because this if will fail. So what's the next stack operation that's going to happen? Yeah.
Would it be like adding this dot count to the...
Well, again, these are not method calls. So we're sort of ignoring things that aren't method calls. So what happens next? Yeah.
Will it just close?
Right, the method returns. So the method is called, it executes some code, which is going to update E and this in ways that we're not modeling right now. And then it returns. So it's just popped off. Okay, now we're back in the array. Now we're back in the loop. So the loop will go, and now it'll go back the second time through the loop. I will be 1. What's going to happen now? Well, first it's going to call addLast. So addLast stack frame comes up again, and then it goes away. The loop goes around again. addLast is called. addLast returns. addLast is called. addLast returns. Now it's been called 4 times. It turns out that the 5th time, this dot count is going to be equal to this dot else dot length, and the if will be executed the 5th time. So what's going to be different this time? Yeah?
You're going to call arrays copy of?
Right, we're going to call arrays.copy of. Now, I don't know exactly what arrays.copy of looks like, but I know that it takes an array and an in as a parameter. So we have a stack frame push for that call to the library node. And it will expect to find in right at the top of its stack frame and a 4 bytes down. And the cool thing is, in this case, a method called a method which called copy of. Would this strategy of looking for in and a at a fixed offset from the top of the stack work if we had a method that called a method that called a method that called a method that called a method that finally called arrays.copy of? In other words, what if this stack frame were actually way up here? Would our strategy still work?
Yeah.
Right, it still works because it's all relative to the top of the stack. So there's a memory location or register or something that contains the address of the top of the stack. And when a variable needs to be looked up, it's done relative to that. Some number of bytes down from the top of the stack. Right? So it's not expecting to find the variables at a fixed location, just at a fixed offset. Okay? Now arrays.copy of will return. And we're back down here. Then we're going to return back to main. At that point, our loop is done. So we're about to call list.set. That pushes the stack frame for list.set. Then set returns. Then we call remove last. Stack frame is pushed. Returns. And what's the last thing that happens to the stack? Main returns. The stack is empty. So that's what's going on as your program is running. Method calls result in stack frames being pushed. So call, 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 and then when they return, they disappear. The stack frames are there to store local variables and parameters. Now, I've given exams in several different kinds of classes where I'll ask people to sketch the state of the stack at some point in a computation. And for some reason, I just don't understand how this happens. This is what I end up, some people do the right thing. If someone says, draw the state of the stack, first thing you should do is draw a stack. And if you decide there are 3 stack frames, you should create 3 stack frames, and you have sort of lighter lines here. There's I, there's X, there's P, there's Q, and all that. That's what a stack looks like. What I get is people doing this. They'll say, okay, here's the stack frame, and here's the stack frame, and here's the stack frame. So if you at least know that all the stack frames are stacked on top of each other in a stack, you're ahead of the game, literally. Yeah.
Can you go over just really quickly what is described as like a stack frame, how it's like xi and like there's q and there's d? Can you quickly go over, because I got kind of confused when you did this.
Okay, so let me neaten this up a little bit. You erase? Okay, so let's suppose we have I and X in this stack frame. What does that tell you about the method the stack frame belongs to? Why would an I and an X show up in a stack frame? No, nothing to do with loops. Or you're sort of taking that clue from I. But why IX and not Z and W? Yeah? Right, there's either a parameter called I or a local variable called I in the method, and there's either an X, that's a parameter, or an X is a local variable. That's what determines what goes in the stack frame. Okay. The only trick is, you can look at the code. You can see what parameters are declared in the header. You can see what local variables there are. The only other thing is this. If the thing you're calling is not a static method, but is either a constructor or a non-static method, then you'll see this in there as well.
Okay, so it's pretty much just parameters, local variables, and this.
Right, and this is a parameter as well. It's just implicit.
Right.
Okay? So if the next method that's called has a P and a Q, and it's static, you'll have a P and a Q. It's just space to store the variables. So yeah, Makes me sad, don't do that. Put your stack frames in a stack and draw more neatly than I thought. Okay. So we went through the program once, just to show you how the stack frames ebb and flow and what goes into the stack frames. So the next step is to see, what is stored into the stack. We didn't see what was stored into the stack, how the actual values are stored and how it changes, or how the heap is used. So let's take a break, and we'll see the answer to that question. Okay, so we're back. Well, it's almost right. We're back in this example, and we're going to repeat it. But this time, we're going to not just see what variables go into the stack. We're going to keep track of their values. So what we're going to have to use is a heap. So I'm going to use sort of the white space over here to the right, below the code, as my heap. So this is the stack, and there's the heap. So the idea is, as your program executes, if anything needs to be saved to a local or parameter, it's just stored directly into the stack right there. And we'll see how that works. Now the heap is more complicated than stacks. Stacks are really efficient. Because to allocate room on the stack, you just move the top of the stack address up by some number of bytes. The heap manager, though, is pretty complicated. It has to find space for objects in the heap, and it has to take care of collecting ones that aren't needed anymore. So the first thing the method does is it's got to create a new array list. So we're going to break it up into two steps. First, it creates the new array list object, and then it calls the constructor to initialize it. So to execute the new, that's what happens. Now, what all happened right there? We haven't called the constructor yet. We just called the new. So, what is that picture telling us? Yep.
That when you create a new myArrayList, it stores space for two variables, else and count.
Okay. So when you call new, an object is created, and objects are always stored on the heap. So out here on the heap, we created that box that contains count and else. Okay? Count and else. Why does this box contain those two variables? I thought variables went on the stack. Yeah? Those are the instance variables of the object. What goes on the stack are parameters and local variables. When you create an object, it has instance variables. So we created a new array list object, and there it sits. If we went back and looked at the code, we would see that it has two instance variables, count and else, short for elements. And so they're stored inside the object on the heap. What's this funny looking line here? This line that goes from here to there to there. Yeah?
That memory address.
Okay, so in Java speak, that's called a reference, but a reference amounts to an address in memory. So what's stored at this spot in the stack is the address of this object, a reference to the object on the heap. And why was this reference stored into list? Yeah?
Because a list is an object, and all objects are stored with references to the actual values.
But why was a reference stored into list instead of to I or to something else? How did Java know to store this reference in the list variable?
Because list is the implicit parameter of the constructor.
No, list is a local variable for main. It's not an implicit parameter to anybody. Yeah.
Because you have the new line with list, so that kind of allocated it the object space.
Right. It says right here, take this object and store it into list. That's what assignment does. So when you see an assignment statement, a variable, something is being stored in a variable. So this says create a new array list and store the result in the variable list. So that's why it goes there. Okay? So let's think about what had to happen. We had to ask the memory manager, the heap manager, to create space for a new array list object. And it did that. It had, the memory manager, the heap manager had to go find out how much space was needed for the instance variables for that class. So this was created. The memory manager handed back, returned an address in memory for the object, and then we had to go find where list is, which is 4 bytes down from the top of the stack, and store the reference there. So anyway, we end up with that. Now we call the constructor. Now, so what will happen when we call the array list constructor? What will change about my diagram? Will the heap change? Will the stack change? Will they both change? Will neither change? What happened last time when we called the constructor? Yeah?
The stack will change?
The stack will change. Someone else tell me, how will the stack change when we call the constructor? Yeah?
It'll add the reference to the object to the stack.
He said it'll add the reference to the object to the stack. That's true at sort of a detailed level, but at a higher level, what's going to happen? Yeah?
It'll add this.
Well, what sort of thing will be added to the stack? What's the word? No. It's two words, and one starts with an S, the other starts with an F. San Francisco. Nope. Stack frame. Every time you call something, a stack frame is pushed. Now, what variables will the stack frame for the constructor contain? Okay? You don't have to guess at this. We can look at the code. Let's find the constructor. There's the constructor right here. So what local variables and parameters does the constructor have? There's the code. You can look at it and tell. Does it have any local variables?
No.
Does it have any parameters? No explicit parameters, but yeah?
That's this.
The implicit parameter. So how many variables will be in the stack frame for the constructor?
1.
1. And that variable is this. So back to here. When we call the constructor, that's what happens. Now, where did this come from? I mean, we understand, well, we understand where this thing right here came from. It's in the stack frame for reasons we just discussed. Where did its value come from? Why is there a reference stored in the entry for this in the stack frame for my array list? Why is it there? I don't see an assignment statement that stores anything there. Yeah?
The implicit parameters?
Well, this is the implicit parameter, but what caused that reference to be stored? This is anything we talked about before because we weren't looking at what went into the stack. Yeah?
The lines that say this.else and this.count, because those variables are...
Nope. That green means we haven't executed any line in the myArrayList constructor yet. This reference was stored here as part of pushing the stack frame. Yeah?
Well, before we even call the methods of our constructor, we do have our instance variables declared just in our definition of our class, what myArrayList is. So maybe those are just...
Well, no, it has nothing to do with instance variables either. Where do parameters, this is a parameter, where do parameters get their values? Does the method that's being called choose the values for its parameters? Are they just picked at random? When you call square root of 8, how does square root get its parameter? Yeah?
It's whatever you give to it.
It's whatever you pass in, right? When you call a method, you say, call this method, and here are the initial values for the parameters. Well, in this case, it's just an implicit parameter. So let's go back and look at the code here. What is the object on which this constructor is being invoked? List. List refers to this thing. It's this object right here that's being constructed. So this reference here is the implicit parameter. So when we call myArrayList, the implicit parameter's value is the same as list. It's the object that's on which the constructor was just invoked. So when a method is called, not only is the stack frame pushed, but each of its parameters is given a value in the stack frame. And the values come from the point of call. The local variables are left uninitialized. Okay, now let's see what happens. The code says this.else equals uint4. Okay? How's the picture going to change now? First of all, what is this.else? Well, what is this? Okay, yeah, it's the object on which the constructor was invoked, but where are we going to find it? Where will we find the value of this? It's right here. Oops. Sorry, I hit my wheel. Okay, we're going to find this down here in the stack frame. And then to do the dot, we have to go find the object it refers to, and in there we find else. So it's referring to this location right here, this.else. And what we're going to store there is a reference to a new integer array of size 4. So that's what we store there. We create an array and store a reference to it. Now, what's going to happen when this.count equals 0 executes? Where is this? Top of the stack. We got to do the dot count operator. So we go find the object. There's the count. What do we store there?
0.
0. Great. Now the constructor is done. What's going to happen? Yeah?
The top stack frame closes.
Right. We're gonna pop the stack frame. And what has happened to list? What does list refer to now? How would you characterize? How is it different? Before, let's go back. Before the constructor was called, list referred to a completely uninitialized object. After the constructor returns, what is list referring to?
An initialized myArrayList object.
Right. It's been initialized by the constructor. And notice how that happened. This and list refer to the same object. So all the work was done via this. But when the constructor returns, list is still referring to the same object, so it sees all those changes. Okay? So it's been constructed. Now what's going to happen? Now that we're through with the constructor, what comes next? The method is going to run along. What's it going to do? What's the next change that's going to happen to the picture? Okay, here's the secret. You guys are way smarter than Java. The Java interpreter is really stupid. All it knows how to do is just very mechanically follow a list of directions and use those directions to modify the stack in the heap. It's not creative at all. So anything the Java interpreter can do, you can do with ease as well. So once it's through with this statement right here, what comes next?
The for loop.
The for loop comes next. And what's the first thing the for loop will do? It says store 0 and I. So it does that. It knows where I is. It's 0 bytes from the top of the stack. So it stores a 0 there. Okay? Then, since 0 is less than 5, it calls list.add last of I. So that's going to push a stack frame for add last. What will be stored? What variables will be stored in the stack frame? Let's go look at the code again. Here's add last. What variables will be in the stack frame for add last? Yeah?
This and E.
This and E. E because it says E right there. And this because this is a non-static method. So, we're going to call add last. And boom. Now, why is a 0 stored next to E, and why is a reference to this object right here stored next to this? How did that stupid Java interpreter know to do that?
Because you told it to.
How did we tell it to store 0? Let's go back. What is telling it to store 0 next to that E?
I is one
Right.
of the parameters.
I is the parameter, the explicit parameter, and its value is 0.
And this is referring to list.
Right. The object in which the method is being invoked is list, which is this object right here. So of course 0 is stored as a value of that parameter, and this reference here is stored as a value of this. Okay? Now what does the stupid Java interpreter do? Yeah?
Check the if statement.
Checks the if statement. It's false, so that doesn't happen. Now what happens? Okay?
It changes the value of else.
Okay, so it goes and finds the else array. So it goes to this dot else, which makes it to this array. It looks into the array location this dot count. So it has to go figure out what this dot count is. That's 0. So it goes right here and stores a 0 because E is 0. Okay, but we're not going to see anything happen when that happens. Then it moves to this statement. What's going to happen here?
Increment count.
It's going to go find this. It's going to go to the object it refers to, look at count, and it's going to add 1 to it. So that changes to 1, and then the method returns. And lo and behold, that object is still hanging around. It's called list in this stack frame, and its count has been set to 1. There's one thing in the list now. It's 0. Okay? Now, we just finished with this line of code right here. What happens next? Yep.
It opens a new stack frame for list unset.
Well, before it calls add last, what will it do?
Increment I.
Yep.
Yeah, it'll increment I by 1.
All right, it'll increment I by 1, because at the end of the loop it does the I++. So that goes up by 1. And now it's about to call add last again. It's going to push a stack frame with 2 elements in it. What will be the values of the 2 variables in the new stack frame? What are we passing as the explicit parameter right here?
1.
1, because it says 1 right there. And the implicit parameter would be
This.
list, which is this reference again. So there's the stack frame for the second call. Now, what's going to change? This if right here will fail again. It's false. What will this do? What will this line of code right here do?
Else at index 1 should be updated.
Right, it'll change this to a 1. And again, you can sort of see that and know that's what's going to happen. Java, being much stupider, is just going to laboriously go through and say, okay, I've got to do an array operation. What's this dot count? It'll go, okay, this dot count is 1. And it's going to say, okay, what is this dot else? And it'll say, okay, this dot else is this array. And what is E? It'll look up E here and see it's a 1. So it'll say, I should store 1 right there. I mean, that's literally what it's doing. It's just grinding through these data structures, following references, looking up the values of variables either on the stack or in an object, and then it's going to change that highlighted thing there to a 1. And then it also, then the next statement will change this to a 2. And then it will return. And this happens again and again. Yeah?
So when it's checking the if statement, when it's doing the this.else.length, will that open up another stack frame to do the length?
Okay, good question. So when it checks this if, okay, it has to look at this dot count, and it sees that, I have to go a little bit further back. It sees that this dot count is 1. And then it has to get this dot else dot length. And the way that would really happen is it'll go this dot else up to the array. And the array carries with it in another field which I haven't shown here, its length. So there really ought to be a 4 stored somewhere up there. So dot length would extract that 4, and then they'd be compared. But it just does this just step by step, following references, looking at variables, pulling out values. Okay, so we just added our second thing, and then it'll happen again. We increment I, so now I is 2. We call the method, this time E is 2, and this refers to the object. It stores a 2 and increments count. Returns. We increment I. We call the method. It stores a 3. Increments count and returns. So at this point, we've got 0, 1, 2, 3 stored in our list. Its count is 4, so it's full. And we still have a reference to it. What's going to happen the next time? So we're going to increment I again. We're going to call the method again. E is 4. This refers to the object. What happens now? You all know what happens now. Someone tell me. What's the very first thing that's going to happen? Yeah.
It finds the length.
Okay, it's going to compare these two numbers. So it'll say, okay, this dot count is 4. This dot else dot length. Okay, this dot else dot length. It knows that's 4. They're the same, so it's got to execute this body here. It's got to make the array bigger. Remember our strategy? Allocate an array that's twice as big and copy the values over. So it's got to call arrays.copyOf. That's a static method. What are the parameters? These things are called the actual parameters. Their values are the actual parameters. So what's this dot else going to be? Yeah?
It's going to be that array.
It's going to be this dot else is a reference to this array. So the first parameter to copy of will be a reference to this array. And what's the value of this parameter right here? This dot count is 4. So it's 2 times 4, or 8. So we're going to pass the parameters to copy of will be n, which is 8, and a, which is the array. Now, I just made this up. I didn't look at the code of copy of. It probably has local variables as well. They'd also be in the stack frame. Okay? So you notice now there are 2 ways, there are 2 references to that array right there. There's one reference that comes from the top stack frame, which is the array being copied. There's another reference that comes from the object. And what does array.copyOf do when we pass it the array A and n8? How big an array does it create? Yeah? Creates an array of size 8. And it copies over the first 4 elements of A into the new array. So it creates a new array. It looks like that. Okay? And then it returns that reference to the method that called it. Now, we're not illustrating what happens when the method returns. But what is going to happen with the reference to this array when we return? What's going to be done with it? Why did we create it? Let's go back in time. What's going to be done with the array that's returned by this method right here? Yeah?
Else will point to an array of size 8.
That reference will be stored into this dot else. In other words, else will no longer point to this thing, it'll point to the new one. So let's go forward in time now. We're about done. So we return from the method, and the returned reference is stored into else. So the object has been modified so that it points to this. What can you say about this guy right here? Yeah?
0 reference object.
There are no references to it. There's no way to get to that object from the stack. That's a definition of garbage. The garbage collector, when it runs, would inspect all the ways, it would look at all the references that start at the stack and find all the objects that can be reached. Every other object is garbage. So this just lost its reference. So we can garbage collect it. So at some time in the future, when the heap needs more space, this garbage will be gotten rid of. But I want to get rid of it right now, so I'll run the garbage collector right there. So it goes away. Okay? Any object not reachable from the stack is garbage because it can't serve any purpose at that point. If there's no way to get to it, there's no way to look at it or modify it. Okay. Then we increment count. Oh, actually, what happened when I hit the space bar there was that the 4 that we were passed initially is now stored into the bigger array, and the count is incremented. So these 2 lines of code, this dot else sub this dot count equals E, modified a different array that time because else refers to something new. This was incremented to 5, and then the method returns. And now the loop is over, and so we're about to call list.set. What will happen now? You should be experts on this by now. What happens when you call a method? Yeah?
Going to change the index to its value.
Well, it's going to, before it does that, what's it going to do? Yeah? It's going to push a stack frame. What variables will be in the stack frame? Okay, this, because the method is not static. What else is it going to have? How many parameters, how many explicit parameters does set take? 2. So there are going to be 3 variables, and plus any local ones. I don't think there are any local variables for set. What will the initial values of the parameters be? How will the initial values of the parameter be determined? Well, let's look at the code again. Let's look at set. Okay? What will determine the initial value of index, the initial value of value, and the initial value of this? What will determine the initial values of those 3 parameters? Yeah?
What we give to it?
What we give to it, right. So one of the variables will become 3, one of the variables will become 8, and this will become this reference right here, because we're invoking the method on list, which is this right here. So we call the method. There's a stack frame for set. Value is 8, because we said so. The index is 3, because we said so, and this refers to that object, because we said so. And then set's going to do this check. It's going to pass the check, so it won't throw an exception. And then it's going to go to else. Uh-oh, I don't see else anywhere in the stack frame. How does Java make sense of this? Our strategy is always to look up else. Index I can find. Value I can find. What the heck is else? Right. Else is just shorthand. It really is this dot else. The compiler would have stuck the this back in. So it goes to this, it finds else, so that's else. Here's index, here's value. So it's going to store 8 at index 3, so that 3 will change to an 8. And then the method returns, and then we call remove last. It just takes the implicit parameter, and its job will be to remove the last element from the list, and remove this element right here, and decrement 5 to 4, which it'll do. Method returns. And now the main is done, and we return. Okay? Here's the thing. There isn't any big idea, complicated idea behind the stack and the heap model. It's just the poor Java interpreter following a limited set of rules to decide what to take from here and store there. It knows how to follow references. It knows where to look inside an object or a stack frame for a variable. It knows how to call a method. It knows how to return. So it's nothing complicated, nothing amazing going on here. It's just a very rather simple computer program manipulating memory the way we just talked about. Now, the last thing I want to show you is, I haven't told you the whole truth about anything, really, but in particular, I haven't told you the whole truth about how an object is represented. So this is more like it. What have I changed about the object in this picture? Yeah?
It points to a stack frame instead of a stack frame.
Well, this isn't meant to be a stack frame, but yeah, it has this extra reference here to this structure right here.
It's a list of its methods.
It's a list, right, so this structure here, sometimes called a virtual function table, first of all, identifies the class of the object. So this object was created by a call to a myArrayList constructor. So by following this reference, we can tell the type of the object. Furthermore, this is where we find the methods, or more really references to the methods that can be invoked on such an object. So if we're trying to invoke the get method on this object, we're going to have to follow this reference and then find get. And again, you just have to know the index of get. And we'll go find the code for get and call it. So every object carries with it a reference that identifies what type of object it is and identifies the method that you can invoke on the object. That's what makes inheritance work. Why is it important to know the type of the object? Where would that information be used? Where can you test the type of an object in a Java program? Yeah. Instance of. So you might say, you might be asking, is this object an instance of my array list? And you would go and say, yeah. Now, this thing here, that's also not the truth. This thing contains a reference. What would you think that this thing would have a reference to? See, every myArrayList object will point to this one table right here. What should this table point to in addition? Yeah?
The array list, like the Java implementation of array, because it uses that.
No, we don't use, we use arrays, not array lists. Yeah? Right, there would be a reference to the supertype object. So every one of these tables points to the table for its supertype. Also, there would be a place in this table that would refer to the interfaces that are implemented by myArrayList, in which there are none in this case. So you've really got a fairly detailed representation of all the objects in the program. And the Java interpreter just knows how to navigate the links and do the right thing. Okay? So I'm not delusional enough to think that you all understand this perfectly at this point. The best I can hope for is when you see it the next time, and the time after, and the time after that, when it eventually sinks in, it won't be in this class, that this will give you a leg up. But also might make it possible to answer a question on the final. So I expect you to understand it at some level. All right, let's end here.